I ask you, what are the main fabrication methods to produce quantum dots with a good control and good quality? You will, like me, tell me that there are two main routes. The first one, which you know very well, is based on the chemistry approach and gives you freestanding quantum dots. However, there is also a second one, which is well known, which is based on the three-dimensional growth mode of strained semiconductor films. If you deposit a highly strained layer on top of a substrate, you will build tiny islands. And if you cap these islands, you will get small band gap clusters which behave as nice quantum dots. Amazingly, we celebrate this year the 30th anniversary of colloidal quantum dots, but self-assembled quantum dots, based on the epitaxial method, have been also discovered in 1984, very close to here, in the Bagneux laboratory of France Télécom, typically 3 kilometers from here. So what I would like to do today is first to tell you how and why this discovery occurred here. Then I will tell you how epitaxial growth has become the main fabrication methods to build embedded quantum dots for optoelectronics. And then I will speak a little bit about some important differences between the two classes of quantum dots, and I will make some brief discussion about the present application prospects of self-assembled quantum dots. So first, let's go back in time in the early 80s, and in order to understand where and why people tried to build strained layers and highly strained layers, it's important to remember what, at that time, people did to develop laser diodes, because it was a key objective in optoelectronics to develop more efficient, more reliable laser diodes. You all know that Zores Alferov got recently the Nobel Prize for the invention of the double heterostructure laser. In such a laser, you place here this orange layer, low band gap layer, in a p-n junction, and this low band gap layer ensures two functions. First of all, optical confinement. It is a waveguide for the lasing mode. And secondly, it plays also the role of the amplifier based on simulated emission. This was the first useful laser diode, the first efficient and reliable one. However, it is not the one we use today. In your CD or DVD player, if you have one, the laser that is used is a quantum well laser diode. Inside this waveguide here, you have now a very thin quantum well which ensures the amplification of the mode. Because of this separate confinement of photons and electrons, because the two layers here play different roles, you can optimize the structure much better. And in the end, this laser diode based on quantum wells works much better and has enabled the development of many applications such as telecoms, internet, optical storage, and also a huge market, which is the pumping of solid-state lasers for the industry. To give you an idea of the improvement that quantum well lasers have brought, you see that here, if you look at the threshold current as a function of the year, you see that after the introduction of the quantum well laser here, progress has been witnessed very, very fast. And in fact, after 90 here, the quantum well laser had become the dominant device on the market. Now, in the around 82, several labs began working on strain layers for lasers. Why? If you look at the sky map here, where the compound semiconductors are shown, you see that, generally speaking, compound semiconductors do not have the same lattice parameter. So if you want to increase the range covered by lasers, for instance, those based on gallium arsenide, you need to add indium. Like that, you will go to lower bandgap material, but for that, you need to change the lattice parameter. You need to put strain in the system. So it works. It's perfectly possible to grow strain quantum wells with a good quality. And so in 82, the goal was really to extend the wavelength range covered by lasers. But after that, people realized that by putting strain, you also tailor the bond structure of the quantum well. And so you can also improve the quantum well properties like that and the laser properties like that. So two labs have played an important role at that time. Sandia, with Osborne, Gourlay, and co-workers, and France Telecom Labs, CNET, with Goldstein, Kiek, and Marzin. So they prepared nice strain quantum wells. Slightly later, two groups in the States demonstrated the first strained quantum well lasers, including lasers at 0.98 micrometers for the pumping of erbium doped fibers. So a very important result here. And very fast, again, strained quantum well lasers became the dominant product within laser diodes. In 84, people at CNET, as well as at JPL, wondered how far this approach could go. And so they decided to put as much strain as possible in the system. So they played with indium arsenide on gallium arsenide. And so I will show you now the lab book to know what happened. This is the lab book in French. The operator here on the MBU is Léon Goldstein, LJ. You have the date, November 84, and you have also the hour. Okay, and what I will translate here, the read pattern becomes spotty during the well, and afterwards becomes cleaner, streaky again, in the barrier. So what did he witness here? We know that when we deposit a strain layer on top of a substrate, there are two possible relaxation passes. You can either, so first of all, you have a coherent growth with no relaxation. But after that, you can either put dislocations on the interface here, or you can build islands on the surface. This is elastic relaxation. And in fact, when you have a lot of strain, such is the case for indium arsenide, gallium arsenide, elastic relaxation occurs first. So what Goldstein had seen was the formation of these tiny islands on top of the surface. After that, he deposited again gallium arsenide on top, and then the surface flattens, and you get a bidimensional layer again. Obviously, it was not the first time that 3D growth of semiconductor layers was observed. However, it was the first time that a careful and detailed characterization of the sample was provided. So they studied the sample by TEM, they studied the sample also by photoluminescence, and what they show is that when you observe this spotty pattern using read, you see here clusters inside the semiconductor matrix, which are indium rich, and as soon as you see the clusters, you see a novel, specific, and intense photoluminescence line. So, and also they could check with TM that there are no dislocations in the system. The layer is perfectly coherent. So now it's interesting to have a look at the conclusion of this very important paper. The conclusion was, I know, mostly written by Jean-Yves Marzin. And so here you have some comments about the fact that the indium-rich clusters have a good crystalline quality. They have a nice and intense photoluminescence. And you have the last sentence here, which tells you these objects are thus proved to be of interest to study low-dimensional objects with good optical properties. So here you have a premonition of the huge development of fine optical spectroscopy to come on self-assembly quantum dots. At that time, there was no suggestion of a potential interest for applications. And there are two reasons for that. First of all, when the quantum dot samples were grown, the wavelength was not always the same. It did not look reproducible. Second, the line was really very broad. So it was difficult to say, okay, such quantum dot arrays will have applications in the field of lasers. And if I say that, it's because, in fact, quantum dot for lasers had been proposed 3 years before by Arakawa and Sakaki. The idea was the following. In a quantum well laser, electrons and holes are distributed, thermally distributed, within the subbands of the quantum well. If we build quantum dots with a small size and perfectly identical, then we will have discrete levels here, well separated with respect to KT, and so all injected electrons and holes will work at the same energy. We will have a very efficient use of the injected current, and so one expects a lower social current and also a better modulation behavior. And so in '85, looking at the broad diffusion spectrum of quantum dots, it was difficult to dream that self-assembled quantum dots would be of interest for lasers. So now, I would like to tell you something which is likely the first time a real application for self-assembled quantum dots was proposed. So I prepared my PhD with Jean-Yves Marzin at CNET. My goal was to grow highly strained short-period sublattices, and I produced also quantum dots at that time. And at the end of my PhD, I had a dinner with Claude Weisbusch from Thomson CSF at that time in Lyon. The restaurant is here, close to the river Saône, a very nice place. And our discussion was dealing with that topic. We have these new objects. What could they be good for? They are not homogeneous. There is a distribution of sizes. But nevertheless, maybe we can find an application for that. So we wrote a lot and sketched a lot of things on top of the cover paper on the table. And at the end of the day, came out this patent where we proposed to use quantum dots as emission centers within poor quality material, within dislocated material. What is the idea? If you work with a quantum well, electrons and holes are free to move. They will go to dislocations where they recombine non-radiatively. For that reason, you cannot build, for instance, a quantum well laser on silicon. It does not work. It degrades extremely fast within seconds. However, now change this quantum well and replace it by quantum dots. Quantum dots trap electrons and holes, and so you quench non-radiative recombination through the quenching of the diffusion to dislocation. And so you hope like that to build efficient and reliable emitters on silicon. Okay, so it was filed in France in around 90. However, this proposal on the interest of self-assembled quantum dots did not, it took time before it became clear to everyone. At that time, indeed, several routes were pursued toward quantum dot ensembles. People had played a lot with nanofabrication. Here you have, for instance, arrays of quantum dots etched from a quantum well. In the end, they were able to get light from such dots. However, the size distributions induced by nanofabrication was not good enough. Typically, 3 nanometer fluctuations in the dimensions. And also, it was extremely time-consuming and expensive. Other approaches were the self-assembling in strain layer epitaxy, and also the growth on patterned substrates. Can be the growth on top of pyramids, or can be the growth at the bottom of V-grooves, as shown by Eli Capone, for instance. In '95, at the end of that period, a workshop was organized by Pierre Petrov and Karl Eberl in Germany. And the topic was growth, quantum dots built by growth on patterned or unpatterned substrates. And the idea was to compare both strategies. And I can tell you that at the end of the workshop, with all the main players of the field, we organized a vote to elect the most promising approach. And there was a large majority of the people in '95 still believing that the growth on patterned substrates would win in the end. Simply because people felt that nanofabrication would be the key to the success. However, it's not the case. It's not the case. The key to the success is, in fact, what nature gives us, the spontaneous formation of something which has a very high quality. And so now I would like to show you three main studies, key experiments, which have, in the end, convinced people that self-assembling quantum dots in epitaxy was the way to go, is the way to go. So the first experiment is based on near-field probes. At the early '90s, AFMs became widely distributed in the labs. And so experiments based on atomic force microscopy were performed noticeably at France Télécom labs and also in Santa Barbara. AFM is nice because you can touch the structures. You can probe very nicely, directly, the size, the shape of your nanostructures. And so you can, after that, play a lot and fast with growth parameters in order to engineer the properties of your quantum dot layer. So at that time, for instance, were published size histograms here, or it could show also in Santa Barbara that the critical thickness here is very well defined. What do we learn also from that? We learn from that the size dispersion is around 10% plus, which is, in fact, it's large, okay. But in fact, it is good compared to what you get simply playing with lithography and etching. So nature gives you something that is more homogeneous than nanofabrication when you speak about objects in the 10 nanometer range. AFM is nice, but I would like to show you also that optical studies can give you very nice, very detailed information about the formation of the quantum dots. The questions we had at that time were the following. How do we go from a bidimensional layer to a three-dimensional layer? What happens in between at the transition? For that, you can grow a sample for which the quantity of indium arsenide decreases or increases from below the critical thickness to above the critical thickness. So you have a region where indium arsenide forms a quantum well, a region where the indium arsenide forms an array of the quantum dots, and so what happens here in between? In fact, the first thing you see when you do that is that the border is not a line. The border is a region. And in this region, you observe both the signature of 2D growth here and of quantum dot formations here. And when you go from the 2D region to the 3D region, you simply decrease the intensity of the 2D signal and increase the intensity of the quantum dot signal. This tells you a lot. What you learn here, and which is confirmed after that by AFM, is that you have on the surface coexistence of regions of 2D growth here with plus 1 monolayer fluctuations, and regions where the quantity of indium arsenide has been enough for the growth of the quantum dot of one quantum dot to occur. In fact, the critical thickness has a meaning. However, it should be defined on a local scale. And quantum dots appear at some specific positions first, simply because you have fluctuations of the deposited quantity of indium arsenide when you play with molecular beam epitaxy. You can see also in these experiments that when you play with the growth rate, the properties of the quantum well do not change. However, the properties of the quantum dots change a lot. The properties of your quantum dot array can be adjusted by playing with dynamical growth parameters, such as the growth rate or such as growth interruptions. As soon as we had understood this point, we fixed the growth rate and so on, and the results of the fabrication process became perfectly reproducible. Now, this was for the first part, understanding how quantum dots are forced. Second part, it is related to the properties of the quantum dots. As long as you see a broad line, you do not know what is inside. What are the properties of single dots? What are the ultimate properties of a quantum dot array, which you would have if the quantum dots were ideally identical? So in 94, we did an experiment inspired from Michel Horitz's work on single molecules in order to study the emission from a single dot. In our case, we cannot that much dilute the quantum dot array. So what we did, we decided to reduce the number of quantum dots by selecting a small number of dots in etched meso structures. And when we move from large mesas containing 10,000 quantum dots, and for which we have a broad line, down to small mesas containing a single dot, we see a drastic change of the emission spectrum. And in the end, we get sharp lines, each related to one single dot. So this tells you a lot. At low temperature, here the experiment was done at 10 K, quantum dots exhibit sharp lines as expected for an artificial atoms, let's say. And also, the inhomogeneous broadening due to size fluctuation is responsible for the broad emission line in quantum dot ensembles. Here again, this experiment demonstrated that such dots are far superior to dots obtained by other approaches. When a single dot defined by etching was studied, the emission lines were always rather broad. So it was the first time that a quantum dot exhibited an emission line much narrower than KT. So nature gives you the best dots, the most intrinsic ones. And the third main event occurring at that time was also the demonstration, the first demonstration of a quantum dot laser by the group of Dieter Bimberg. Dieter Bimberg, in collaboration with the Joffe Institute, grew a sample for which quantum dots were placed in a PN junction. And they could show that at low temperature, 100 K here, the laser displayed a very low threshold and a temperature insensitive behavior. It degraded at that time somewhat when you went when they went to room temperature, but in the next months, the properties of their lasers improved a lot. Why is this event important? Don't forget that the main motivation for the fabrication of dots at the first place was to improve lasers. And here, it was very important that the first quantum dot laser was, in fact, was based on self-assembled quantum dots and not other fabrication techniques. So these different contributions made all together convinced, I think, the community of the interest of self-assembled quantum dots. And at that time, everything went very, very fast. So much work has been done on development on novel material systems, as well as fine optical spectroscopy, and also efforts on devices. So I jump now 20 years ahead in order to speak a little bit about what are the application prospects of quantum dots today. In order to discuss that, the first thing I have to say is that a quantum dot is not an isolated atom. It displays very sharp emission lines at low temperature, but when we increase the temperature, we increase the population of phonons inside the phonon bath, and we see here that single quantum dots exhibit on the PL spectrum very broad phonon-related wings. At room temperature, the emission line width of a single dot is typically 20 MeV. This tells us many things. First of all, we are very far from the original dream of Arakawa and Sakaki. We will never get, at room temperature, very sharp emission lines for ensembles of quantum dots. So I have to say that the quantum dot laser revolution did not occur. We know it. But it will not occur because we have inhomogeneous broadening. OK, that's it. But we have also an intrinsic limit for quantum dot lasers. We have this homogeneous line width related to the coupling to phonons. So what we can dream about today is some specific applications for quantum dot lasers. So there are several which work very well. For instance, a company has been recently, 2 or 3 years ago, started in Japan, funded by by Arakawa and colleagues. And this company targets the fabrication of quantum dot lasers for optical telecommunications at 1.3 micron. Here, the reference quantum well laser is based on indium phosphide and has a huge temperature sensitivity. By moving to quantum dots, they can use gallium arsenide as a base material with large barriers here, very nice electron and photon confinement, and the quantum dot lasers on gallium arsenide display properties which do not depend upon temperature. This is very interesting for telecom companies because they can now build low-cost lasing modules with no need for a cooler. So they reduce by a large amount the cost of the emission modules. So it's practical considerations, but very important for the commercial future of quantum dots. Another very encouraging result, I think, is a recent demonstration of low-threshold quantum dot lasers directly by epitaxy on silicon chips. This has been done 2 years ago by University College London, and this is really very attractive for the integration in the future of 3-5 sources on silicon. And finally, if I have 3 minutes, sorry. Finally, it is important to see that the nice optical properties, sorry about that. OK, so quantum dots have also their nice atomic-like properties at low temperature, which can be used and will be used in the future to develop novel quantum optoelectronic devices such as single photon sources. Because they have sharp lines, you can combine such solid-state emitters with optical microcavities in order to tailor the spontaneous emission of the quantum dots very efficiently. So this is something that we started in 95, 96, typically. And we could show for the first time, for instance, using this combination, that it is possible to enhance the spontaneous emission rate of quantum dots coupled to a cavity mode. In that case, it was in a macropillar. So why is it interesting, and what can we do with that? In fact, spontaneous emission control is very important for building single photon sources. A single photon source is a device that is able to emit light pulses containing one and only one photon. So you prepare such non-classical states of light by having somewhere a quantum emitter, such as a quantum dot. And if you are able to prepare such a non-classical state of light, you will have within reach nice applications, such as quantum cryptography or optical quantum computing. However, for these applications to become reality, you need definitely a high efficiency. You need to put actually a single photon in the mode, and you need all single photons to be prepared in the same quantum state. So what you need here is single mode spontaneous emission. So how to get that? I will give you only one example that is based on the Purcell effect. Sorry. So what you can do is the following. You have your quantum dot able to emit photons one by one. You place it here in a cavity in resonance with the fundamental cavity mode. And thanks to the Purcell effect, you have an enhancement of the light emission into the cavity mode, and most photons are funneled, are prepared into this single mode. So this works very well. And for instance, after our initial demonstration with, let's say, typically 40% of the photons collected, last year at CNRS LPN, the group of Pascal Senlar could show that by playing with this approach, it is possible to put 79% of a photon per pulse. Okay, so you have, like that, by playing with cavity effect, a novel device that is actually extremely efficient and extremely interesting for practical application in the world of quantum information processing and quantum communications. And maybe a final slide to show you that it is not the only geometry that can be used. Okay. I will conclude with that because Hey, does not help me. Huh? Okay, this is the kind of objects we develop nowadays in Grenoble. Here, you have no cavity. You simply have a dielectric waveguide here with a tiny diameter around lambda over n. And if you place a quantum dot inside this waveguide here, you put 95% of the light inside the single mode of the waveguide. After that, you increase the size of the mode here using an adiabatic taper here, and you have a wonderful coupling to a Gaussian beam with a very narrow divergence. So these kind of objects are extremely interesting in view of future applications, not only to build single photon sources, but because these objects have no cavity, they can be used as a nice interface to convert material qubits trapped, coded on the quantum dot exciton here, into flying qubits, photons, and vice versa. So it's likely that this system, a single dot in a photonic wire, will be one of the best quantum interfaces for quantum information processing in the future. So I'm ready to answer to your questions if you have some on this topic. And with this, I would like to simply put that slide because over the 28 years I've been working on quantum dots, I had the opportunity to collaborate with many, many people. I acknowledge here only some of them. I should have acknowledged many, many others. However, it has been a wonderful period of my life. Thank you very much for your attention.